Good day, my friends. I hope you're having a good day. Today we're going to talk about air movement. It is the last part of this chapter. So your test is going to be this Friday. You must have it done by 11:59 Friday. I will tell you more about that at the end of the lecture. Today we're talking about air movement, chapter 15.4. By the time we're done, you should be able to list the properties of the air currents within a convection cell. You should be able to describe how high and low pressure cells create local winds and explain how several types of local winds form. And you should be able to discuss how global convection cells lead to the global wind belts. This is a lot of information, so it's going to be a little bit longer of a lecture than we usually have. So just be prepared. So we should know by now that air travels in a convection current. As the warm air rises, it leaves kind of a gap at the bottom, and so it creates a low pressure zone close to the ground. The air then gets up to the top and it moves horizontally across the top of the troposphere. That movement of the air across the top of the troposphere is called advection. Okay, so air comes up. We have advection where it goes across at the top. The air then cools down, and as it cools, it begins to descend or go down or sink. This air creates a high pressure zone because all that air is coming down and putting pressure on the ground. So where it comes down close to the ground, it creates that high pressure. As the air moves then from high pressure to low pressure, it creates wind. Because remember, this low pressure is like leaving a gap down here. So the high pressure was going to push that into, or some people say that the low pressure kind of creates almost a sucking of the air from the high pressure to the low pressure. And that creates wind. The greater the air pressure difference, the stronger the wind, which makes sense. Air moving at the bases of the three major convection cells in each hemisphere, north and south of the equator, are what create the global wind belts. We're going to talk about those a little bit later. The convection current is in our atmosphere is what's responsible for most of Earth's weather. Remember that warm air holds more moisture than cold air does. So as the air heats close to the surface here, it picks up moisture from lakes and rivers and streams and even mud puddles. And because it's warmer, it holds quite a bit of moisture. As it warms even more, it rises. Well, as it rises, it starts to cool. And that cooler air can't hold all of that moisture in water vapor form. So that water vapor starts to condense. Remember, we said that there are little bits of material in the atmosphere. This is where they become important. Little bits of dust and fecal matter and dirt and all kinds of different stuff just floating around. Well, the water vapor then condenses on those little bits of material in the atmosphere, which form our clouds. And when those clouds condense enough, then that creates precipitation. The cool air sinks, and then as it sinks, it creates that high pressure cell, which creates the wind. It gets moved across the surface where it warms up again, and the whole cycle starts all over again. There are four major kinds of breezes that we're going to talk about. We're going to talk about a sea breeze, a land breeze, a mountain breeze, and a valley breeze. They're named for where the wind starts. Very important here. They are named for where the wind starts. Now remember, water has a high specific heat, so that means it cools more more slowly, and it heats more slowly than the land around it does. That creates high and low pressure cells, which is what causes the local wind. So this water is going to heat up faster or slower. I don't know why I keep saying faster. I'm sorry. The water is going to heat up faster than the land. I did it again. Water is going to heat up slower. Water is going to heat up slower. Water is going to heat up slower than the land does. It is also going to cool slower than the land does. I already did that one. I'm sorry, guys. This is weird. Sea breezes come from the cooler ocean across the warmer land. They occur when there is a temperature difference between 5 and 10 degrees Celsius, or between 9 and 18 degrees Fahrenheit, with the land being warmer, and they can blow at between 10 to 20 kilometers per hour, or 6 to 12 miles per hour. These are going to occur most often in the summer when the land is hotter. Land is going to get hot. The ocean is going to be cool. This air is going to rise, and the air from the ocean is going to rush in underneath it, causing a sea breeze. Land breezes come from the warmer ocean across the cooler land. They occur when the ocean temperatures are higher than the land temperatures, and they can actually warm the air that is over that land that is close, or over the land that's close by the ocean. That's why living by the ocean, you have more moderate climates, like down in Georgia or down in Florida, along the southern coast of Texas and Louisiana and Alabama and California. Okay, land breezes are going to occur most often in the winter because the land is going to be colder. That means, remember, this is going to cool slower, so the ocean is going to be warmer. So that warm air is going to push over the land, and the cold air is going to rush in from the land to the ocean. Land breezes, because it comes from the land to the ocean. Monsoon winds are just really huge land and sea breezes. They occur most often around India, where the land is really, really hot in the summertime, and it's right next to the sea. If you look here, you can see that the winter monsoons, you have a high pressure on land, lower pressure is out in the ocean. So it's going to create the winter monsoons here, and in the summer monsoons, it's going to move from the high pressure in the ocean to the low pressure in the land for the summer monsoons. Monsoons are very important for some areas because these are what provide rains for countries that have low rainfall. They look forward to these monsoon seasons to be able to get enough moisture on their in the ground to raise their crops and things. The temperature difference between mountains and valleys create mountain and valley breezes. I bet you're surprised by those titles. Air on the mountains are going to heat up faster than air at the same altitude over a valley. So during the day, the mountain heats up faster than the valley does. The warm air rises and pulls that air from the valley to the mountains. So usually during the day, you have a valley breeze. Okay. The opposite happens then in the evening when the sun sets. The air over the mountain cools quicker. So the cooler air is pulled down the mountain by the warmer air coming up in the valley. Katabatic winds form over high plateaus. They're almost always surrounded by mountains. They are valley and mountain breezes. They're usually, again, like the monsoons are like monster land and sea, or land and sea breezes. Katabatic winds are the monsoon of the valley and mountain breezes. Air is going to rush over the plateau really quickly and rush down the ledge. The bigger the temperature and pressure difference between the plateau and the valley below it, the stronger the winds are going to be. Then we have the Chinook winds. These happen at large mountain ranges where wind comes off the ocean. So they're going to be the mountain ranges that are closest to the oceans. And this is what causes a lot of our deserts in the United States, especially. The side that the wind comes from is called the windward side of the mountain. The other side of the mountain is called the leeward side of the mountain, and that's where the air is going to sink. So what we have is we have usually an ocean over here, and the warm, moist air gets pushed across here and gets pushed up the valley. It as it rises, it starts to cool and it starts to create clouds and rain or snow, depending on the season. All of that rain or snow is going to fall on this windward side of the mountain. By the time it reaches the top of the mountain, it has lost most of its moisture and it has started to get hotter. Then the air moves down the air moves down the mountainside. It moves down the mountainside. It starts to warm up. It creates really strong, dry winds. Remember, it's dropped all of its moisture over here, and so it's really, really dry, and it's warming up as it comes down the mountain. This can actually raise the temperatures of the areas by 36 degrees sometimes. But it can also dry up that area because that warm, dry air is moving across. This is what causes what is called the rain shadow effect. This is what creates our deserts because the moisture is all on this side, but it's really, really dry on this side. Then we have several different kinds of winds. We've talked about the Chinook wind. This is the Santa Ana winds. These occur mostly around Santa Ana, California, because it starts in the Great Basin. The air in the Great Basin cools down. It creates a high pressure front there in the Great Basin, which pushes air downhill, and that because of the Coriolis effect, that air is moving clockwise in the northern hemisphere, which is where we are. Our air moves clockwise, remember? Air pressure and temperature rise as humidity decreases. And the air is warming up as it's moving down the mountain. The wind is then going to blow across the desert, and it's going to blow through the canyons that are between San Gabriel and San Bernardino Mountains, it's moving toward the ocean. This is kind of the opposite of the Chinook winds. This is the Santa Ana winds. If the winds happen at the end of a drought season, which they usually do, if a fire happens to start when these winds are blowing, the winds can cause this fire to spread out of control, which is why California has been having so many terrible, terrible forest fires at the end of summer. So in the desert, we have what are called desert winds or haboobs. In the desert during the summer, we have really, really high temperatures, and everybody says, duh, right? Well, those high temperatures can cause high winds. The winds are going to pick up that dust and the sand, all the dirt and stuff as they move across the desert, and they can form one of two things. They can form a haboob, which is what this looks like. This is a picture of one. Basically, it's a giant dust or sandstorm, and it's from the downdrafts on the front of a thunderstorm. They can also form dust devils, which, if the air starts to circulate, they're like they almost can look like little tornadoes of dust and dirt. So now we're going to talk about atmospheric circulation. We have 3 different zones of circulation in each hemisphere for a total of 6 different zones. You need to remember that air cools and sinks, and it creates a high pressure zone, and it warms up and rises, creating a low pressure zone. So the cool air is pulled toward the low pressure zone at our equator. Okay, we have our equator heats up faster than the rest of the planet does because of the sun's radiation. I feel like I missed a slide. You guys, this is going to be wonky. We did. Solar radiation at the equators heats the air at the equator really fast, which creates that low pressure zone. We've already talked about that. The air then rises to the top of the troposphere, like right here. The air rises to the top of the troposphere, and then it splits in half. Half of it goes north, half of it goes south. Okay, so half of it is going to move toward the North Pole, half of it's going to move to the South Pole. That cool air is going to sink then when it moves over here, and it's going to create a high pressure zone. That cool air is then going to be pulled toward the low pressure zone at the equator. Because our Earth rotates. If our Earth didn't rotate, we'd have one big cell, and that would be it. But our Earth does rotate. So we have to take the Coriolis effect into account when we're talking about air circulation. We talked about the Coriolis effect back when we were talking about water circulation and that kind of thing. We're going to talk about the Northern Hemisphere because the Northern Hemisphere and Southern Hemisphere are exact copies of each other. Since we're in the Northern Hemisphere, that's the part we're going to talk about. Air rises in the troposphere from the equator. It appears to move to the right. It's not really moving to the right. It's just the way our planet rotates. Because our planet rotates, it looks like it's moving to the right, hence where the Coriolis effect comes in. At about the 30-degree latitude, the air meets air that's coming from the poles. So it's going to meet cooler air. As it meets that cooler air, it's going to descend back down closer to Earth and get pulled toward the equator again. This convection current that occurs between 0 degrees latitude and 30 degrees latitude is called the Hadley cell. The next cell is called the Ferrel cell. It's going to occur between 30 degrees and 60 degrees. The air is going to sink here at the 30 degrees, just like it sinks for the Hadley cell. It's going to sink at the Ferrel cell. It's going to warm up as it goes across the land, moving north. And then because it's warmed up enough, it's going to rise at that 60 degree north latitude. That's going to be called the Ferrel cell. And the last cell that we have in the northern hemisphere is the polar cell. It's going to go from 60 degrees north to 90 degrees north. The warm air is going to rise with the Ferrel cell's air at 60 degrees north, and it's going to sink over here at 90 degrees north. Because it gets cold enough, it sinks, and then it moves along the Earth's surface until it warms up again, and at 60 degrees it rises. Now there are duplicates of all three of these cells in the southern hemisphere. So we have the Hadley cell, we have the Ferrel cell, and we have the polar cells. Okay? The only difference is that the Coriolis effect, instead of making the air appear to move to the right in the southern hemisphere, the Coriolis effect makes the air appear to move to the left. Now the global wind belts are right along those same cells. It's the wind from the cells that create the global wind belts. Winds are almost always going to be steady. They're going to always move from high pressure to low pressure horizontally along in those same latitudes. Again, we'll look at the northern hemisphere because that's the hemisphere that we are in. So in the Hadley cell, remember the air is moving from the north to the south. And remember, it looks like it's deflected to the right because of the Coriolis effect. So the winds are going to blow from the northeast to the southwest. This was really good back when we had sailing ships that came from one country to another. They almost always sailed from northeast to southwest. So it was really good for those sailing ships that the winds in those areas blew in that direction. So those winds became known as the trade winds. So trade winds are from 0 to 30 degrees latitude. Then the Ferrel cycle, in the Ferrel cell, the winds are going to move from the southwest to the northeast. So because they start in the west and blow to the east, they are known as the westerlies. Polar cells, the wind is going to move from the northeast to the southwest, so they are known as the polar easterlies. Remember that names of winds the winds are named for the direction in which they begin. So where they start. That's why the polar cells start in the northeast, so we call them easterlies. In the Ferrel cell, they start from the southwest, so we call them the westerlies. Two more things we have to talk about, and then we will be done. I know this is a lot of information, and I know I'm talking about it fast. I wish we were in person so that I could answer your questions and stuff as we were going along. So the place where polar cells meet, the Ferrel cell, is called the polar front. It's right here. And what we get is the warm, dry air from the ferrule cell is going to run into the cool, moist air from the polar cell. And this is going to create lots and lots of different kinds of weather. This is where we're going to get a lot of our rain, a lot of ours in the winter. I'm sorry, rain in the summer and a lot of snow in the winter. So that's why we get the rain and the snows that we do. A jet stream, if you look right here, we have a polar jet and we have a subtropical jet. A jet stream is just a fast flowing current of air at the boundary between the troposphere and the stratosphere. So they're going to be right up at the top of the troposphere. Jet streams are going to occur where there's a large temperature difference between the two air masses. So the most powerful jet stream, which is most people just call it the jet stream, is going to occur here between, again, the polar cell and the ferrule cell. This is the one that people talk about when they talk about the jet stream. It moves south in the winter and it moves north in the summer. And it's between about 30 degrees north and somewhere between 50 and 75 degrees north. Okay, there is also something called the subtropical jet stream. It is not nearly as strong because there's not as big of a temperature difference between the ferrule cell and the Hadley cell here. So this isn't as big of a jet stream as the jet stream or the polar jet stream. Okay. So tomorrow you are going to do the study guide over this section. You will need to get that done tomorrow, Wednesday. Thursday, you should practice for the test. There will be a study guide available. It should say test review. There will be a Kahoot available. And there is a Quizlet that will be available. You need to use those to study for the test. You need to study for the test on Thursday because at 7 o'clock Friday morning, those will all close and I will not open them again. At 7 o'clock Friday, the test will open and you have until 11:59 Friday night to get it done. I will not open the test once it closes on Friday. You will have one attempt to complete that test. If you open it and you go beyond that 75 minutes, it will automatically close and I will not open it again. Do not close it in the middle of the test. If you do, I'm not opening it again. You have one attempt. You have 75 minutes from the time you log on until it will log you off. That is an entire class period and more than half of another class period. So make sure you study on Thursday. Be ready for the test. You have, I'm going to say it one more time, you have one attempt of 75 minutes to do this test. Don't ask me to open it again. Thank you. Have a wonderful rest of the day. See you. Bye.